Hello everyone, my name is Mei Li and I'm a math major with minors in data science and statistics in the honors program. My honors thesis is on the US housing market from 2000 to 2024 and it involves modeling and forecasting Southwestern home values using time series analysis techniques. Okay, before I begin, I'll give a brief overview of my talk today. First, I'll be going over the background of this research project and where the data came from, the methods, results, conclusions, and possibilities for future study. My research objectives were: can we model and forecast future home values based on available data? Did home values continue to follow historical trends during the COVID-19 pandemic? And is there a pattern of influence from home values in one city to nearby cities? So the data that I used is from Fannie Mae, the Federal National Mortgage Association, and this is a government-sponsored enterprise that was founded in 1938. Their main purpose is to create affordable housing and maintain liquidity in the housing market. So Fannie Mae has very large data sets that tracks a portion of their mortgages since 2000. The exact selling price of the home, however, is not included in these single-family home data sets, but we did have original UPB, which is the original unpaid principal balance of the loan, and then we also had LTV, which is the loan to value ratio. So to calculate the housing valuation, we divided UPB by LTV. I also used long-term interest rates from the OECD, the Organization for Economic Cooperation and Development. So we primarily focused on 4 Southwestern cities. These are Las Vegas, Phoenix, Los Angeles, and San Diego. And you're probably wondering, why did we choose these cities? Previous research done by Gupta and Miller in 2010 found that home values in Southwestern cities, Las Vegas, Phoenix, and Los Angeles, may influence one another. So Gupta and Miller looked at the time series relationship in these cities from the years 1977 to 2008, and they used Granger Causality test, which is just essentially a hypothesis test that is used to determine whether one time series is useful for forecasting another. Since this study, there's been the 2008 housing market crisis as well as the 2020 global pandemic, which may have changed the dynamics of home values. So we are interested to see if we observe a different relationship between these Southwestern cities that Gupta and Miller looked at, as well as San Diego, which is a nearby city. Okay, so now we look at the methods that were used to carry out this project. So the programs that were used included Python, which is a general purpose programming language and an industry standard for data science and analysis, as well as Jupyter Notebook, the web-based computer platform. And then JUMP, a very powerful statistical modeling software, was used for visualization. So this snippet of code here is a small piece of a for loop that I wrote to take random samples from the Fannie Mae data. Okay, so this is a simplified visual of what the wrangling entailed. So the performance all zip was a file that was downloaded from the Fannie Mae website that had all the quarters from 2000 to 2022, quarter 2. So there were 91 CSV files in performance all zip, and from each CSV file, we took a random sample of 500 for each city. So this computation took several hours to run. It actually ran overnight, and in the end, we had 45,500 rows for each city. So time series analysis uses data that is collected over time, and these observations tend to be related to past observations. Simple methods like linear regression require observations to be independent, and for home values, this quarter's values tend to be related to last quarter's values. So this is why we needed to use time series analysis. The type of modeling we used is called SARIMA-X modeling, which stands for Seasonal Autoregressive Integrated Moving Average Exogenous Model. This SARIMA-X model is actually a combination of 2 basic time series models called the AR, the autoregressive model, and the MA, moving average model. So essentially, after combining the AR and MA model and integrating to achieve stationarity, as well as accounting for seasonality and exogenous variables, we get the SARIMA-X model. And then similarly to Gupta and Miller, we also did Granger causality testing to see if we could still detect whether or not one city's home values affect home values in another nearby city. This slide depicts the average home values of the 4 cities from 2000 to 2022. Some immediate observations to make include the fact that Las Vegas seems to have the lowest overall average home values when compared to the other 3 cities. In 2007, Phoenix seemed to have a spike in average home values until there was a dip in 2010. And then finally, in 2021, Phoenix also had a sudden spike, reaching an all-time high in home values, while the other 3 cities had gradually increasing home values. So the order of the SARIMA model can be determined in 2 ways. The first way is looking at the autocorrelation functions after differencing. So for example, we have the home prices of Los Angeles. So after differencing once, we achieve stationarity, which just means that Compared to the graph on the left, the graph on the right has no overall increasing trend. And then the autocorrelation functions are two different ways to look at the relationship between an observation in a time series and its prior time steps. So what we're looking here at is the height of each lollipop. If the lollipop is outside of the confidence band, that correlation at that time lag is significant. So for example, the third lollipop is the only one that is outside of the confidence band. So this means that the correlation at time lag 2 is significant, and this is indicated by AR2. So the order of the Surima model can also be determined by using automated functions. And Python has an AutoArima function that would select the model with the lowest AIC and just spit out a summary of results. So here's an example of the best model chosen for Los Angeles and its results. So these were the model results for each city. And when reporting the model results, there are two sets of parentheses. The first set of parentheses represents the non-seasonal component, and then the second set represents the seasonal component. The little p, which is the AR component, tells you how many past observations you're regressing on. The little d is the order of differencing, so how many times did you need to difference to achieve stationarity. The little q is the MA component that tells you how many past errors the model regresses on. And then the capital PD and Q mean the exact same things as the lowercase pd and q, but they are for the seasonal component. For the models without long-term rates as an exogenous factor, so this second column here, they were all different once to achieve stationarity. Las Vegas and San Diego both have 0 for little p, which means that they were not regressed on any past observations. Las Vegas also has a seasonal component, which means that it was regressed on the observations 1 year ago. Los Angeles has little p equal to 2, which signifies that we are regressing on the past 2 observations. And Phoenix has little p equal to 1, which means we are regressing on only the past observation. So for the models with long-term interest rates as an exogenous factor, so this very last column here, there was no differencing at all, but instead there were seasonal components added to Los Angeles and Phoenix. Below the table, we have an example of the Los Angeles model with its coefficients. Here we can see that the mu is positive, and then we have negative coefficients for the past observations. These negative coefficients indicate something we refer to as the mean reverting model. The first graph on the left shows our Los Angeles forecast without interest rates. The black line is the data that we actually have, the green is the upper confidence bound, the blue is the actual forecast, and the red is the lower confidence bound. Here we can see that our forecast predicts an upward trend in home values. Our test set stays within our confidence bounds, but there seems to be a sharp increase in 2020, followed by a sharp unexpected decline. This second graph shows our forecast when we take our exogenous variables long-term interest rates into account. The upper confidence bound seems to follow the average home values closely at the beginning, but as we move further into the future, we always lose predictive power. The lower confidence bound and the actual forecasted home values seem to detect a sudden dip in 2020, which didn't actually occur. This potentially indicates that there's a deviation from historical patterns of how interest rates affect home values. In San Diego, we observed home values fall outside of our confidence bands, which indicates that there's major increases in home values, which statistically and significantly differed from historical patterns. This was also seen in Phoenix. So in other words, these increases of home values post-2020 could not have been predicted based on market behavior since 2000. Las Vegas, however, seems to follow the opposite pattern, though it's not immediately clear why. They did not experience the same early pandemic boom as these other cities. For the Granger causality results, only 2 tests were significant. So San Diego Granger causing Phoenix and Las Vegas Granger causing Phoenix. All other tests were not significant. So for model results, when interest rates were included as an exogenous factor, no differencing was required. So we concluded that interest rates can explain non-stationarity in home values, and Los Angeles and Phoenix exhibit seasonal effects. For our forecasting conclusions, we found that housing values since 2020 diverged notably from historical patterns. Specifically, there were increases in Phoenix and San Diego, while in Las Vegas there was a decrease. So for our Granger causality conclusions, Gupta and Miller's observation that Los Angeles Granger causes Phoenix is actually no longer detectable. However, their finding that Las Vegas Granger causes Phoenix still remains detectable. So some possibilities for future studies. Throughout this entire project, we use the mean rather than the median. And the mean is more closely related to total home value within the city, and the median would be a more typical home value. Another idea is, can similar patterns be detected in other clusters of cities? So instead of southwest, maybe northeast, southeast. Another possibility are models that use Bayesian approaches. And then finally, what other exogenous variables can improve the model? So we primarily use long-term interest rates, but perhaps demand could be another exogenous variable that improves the model. That is all I have. Thank you so much for listening to my presentation.